Okay, so this moves us into section 9.4, applying the phasor relationships to the circuit elements. This section, actually the next section, is really the meat of this chapter. Everything that we have been doing leads up to these last two sections, because we want to, all of this math that we just learned, we want to be able to apply it to a circuit and use it, and these phasor relationships are actually going to make our circuits a lot easier to analyze than how we did it in chapter 8, which was by the second order differential equation. So let's go back for a moment and look at a circuit with just a resistor in it and recall our Ohm's law. And so I'm going to remind everybody that there is a sinusoidal source driving this circuit right now. So a V that equals some amplitude cosine omega t, and it may have a phase difference. And there's also an I in this circuit, and the I, as a function of time, equals some I max value cosine omega t plus a phase. So the phase really just means that at some particular instant in time, that I've called a zero reference point, if I've called this the zero reference point, my sine wave is not starting right here, but it's starting somewhere different based on some phase reference point that we've described. So that's all it really means. So this is the most generic case of saying that I have a phase phi in here. But normally, actually, when we talk about resistors, we'll put the resistor along the real axis. But anyhow, if I have a voltage and I have a current, they're in phase with each other. The voltage, if I were to write it as fully as a function of time, you would have V cosine omega t plus phi equals R times I, and the I would be also a cosine omega t plus phi. There wouldn't be anything different because we learned in Ohm's law that if R is fixed, if I is at a maximum, V is at a maximum. It's a linear relationship. The I and the V are what we say in phase with each other. So in our vector notation now, our phasor notation now, phasors are like vectors, we have that same linear relationship conveyed in our phasor notation. So this is the function of time notation, and this is the phasor notation, which is a function of frequency. So remember the omega t is always implied in here, although not explicitly written. So we will see coming up how that makes it easier for us. So now if we move on, I see my little markers are off a little. Let me move this. There we go. If we move on to what happens in our other passive components, our resistor and our inductor, our capacitor and inductor. Let's look at inductor next. So inductor has a relationship V equals L di dt. That's sort of like Ohm's law, V equals IR, where now my constant of my linear constant is this inductance value, but instead of being voltage and current directly related through a linear constant value of L, it's related by the rate of change of current. And so it's, in a way, it's sort of a different form of Ohm's law, although it's not Ohm's law. It says the inductance relates the voltage and the rate of change of the current in the circuit. So in the time domain, we write it this way. And this section of your textbook proves that in the frequency domain, it can be written this way if you have, if and only if you have assumed a sinusoidal current that looks like this. So here's our sinusoidal current oscillating at omega with some arbitrary phase included. And since V equals L di dt, we go ahead and we do the derivative right here. This is what it turns out to be. It becomes a sine something with a negative sign in it. We apply trigonometric identity, and then we continue doing the math. So here it is in a function of time. I switch back down here in the next, because we want the phasor notation in the end. We switch it now into our phasor notation, which is our exponential notation, keeping in mind that E to the j omega t is always implied in this in here. And so continuing on, bringing out the 90 degrees phase shift. Now remember that e to the j 90 is like putting j in front. Here it is. E to the j 90 is the same as putting a j in as a coefficient. So ultimately then we get the phasor notation for an inductor as j omega L I. So the V's and the I's are both phasors. They have an angular portion associated with them. As a result of this, we remember in the resistor circuit, V and I are pointing in this, the phasors are pointing in the same direction. They're in phase with each other. But this portion, this J in front, is incurring a 90-degree phase shift. So V is I plus 90 degrees. And when we draw our phasor diagram, we see that. So our I might be at this angle, but the V will be 90 degrees further counterclockwise. What that means is that in a circuit, when I is a max, V is not a max. If I put it on the real axis, you can see that. I'm going to show you an example to make you to ensure that you see it. So the points in time, in an instant in time, where I is a max is not the same as where V is a max, like in a resistor. So now keep in mind that these vectors, these phasors, are rotating at a rate of omega radians per second. So they are rotating in a counterclockwise orientation. And if you think about that, these vectors are rotating, and we're taking the cosine of it every single time to find the instantaneous value. As these vectors come back around towards my starting point, my real axis right here, V is here and I is here. And the first one to cross this real axis is V. So we say that V leads I. And if we were to look at what was happening in time, that would mean that the voltage in the inductor, doing something like this, voltage in the inductor, this is at 0 degrees, this is 90 degrees, this is 180 degrees, 270 is here, and 360 degrees to complete a full cycle, right? So this is V in the inductor right here, and then V leads I, but you would see that I in the inductor in time would be doing something like this instead. This would be I in the inductor. Can't draw it very good. But so the one that crosses 0 first is V, and then I, this is I in the inductor, I crosses 0 90 degrees later. So when V in the inductor is at 0, I is at a maximum. And if you think about our circuits, if we had an RL circuit, for example, going back and refreshing your memory just to show you how it makes sense. So the current in the inductor is what current in the inductor behaves as an exponential type behavior. So as the circuit time progresses and 5 LR time constants go by, the current will be at a maximum through the inductor in the steady state. And then similarly, the voltage in the inductor does an exponential decay. And so when I is a maximum, V is a minimum. So when I is a maximum, V is a minimum. And you can see that in the sinusoidal behavior of the circuit. So that's trying to make physical sense of what's happening. So we have a similar thing happening with a capacitor now. and we can go through a derivation as well. This, we have I equals C dV dt. So this is C, how C behaves in sort of an analogy to Ohm's law. So I and voltage are related by the rate of change of voltage in a capacitor. And when we go through the math, we'll see the frequency domain relationship for what I and how I and V are related. And again, we have a phase shift term here. And in this case, the angle of I, if I have, for example, I at 0 degrees, it's going to equal j omega c, and V, but V is going to be at some other angle. Let me restate that. I had a little distraction. I'm going to restate that for a moment and show you what I mean. So delete that. Rewrite it again. Okay. So in a capacitor, we have this relationship here. So if by any chance I put V at 0, then I would equal j omega c, and then I said if I had V at 0, I would put it at 0 degrees, and then I would be, by virtue of this is like putting something at 90 degrees here, omega c, that's the magnitude, and then something at 0 degrees, and it would say that I would then equal omega c 90 degrees. So compared to C. So I is ahead of V by 90 degrees. And so we'd say in this case, because we are rotating around at this angular rate, I will cross the real axis first, so I leads V in a capacitor. So you'll hear sometimes this leading and lagging expression, or this leading and lagging terminology in RLC circuits. So in this, in the circuit, I leads V sub C in the capacitor. And to make sense of that, if you recall back, that the voltage in the capacitor charges up, and at the same time the current in the capacitor gets less and less, right? And so in time, with an AC signal now rather than a step response, and if I'm looking at it in time with an AC signal, voltage in the capacitor could be doing this, and then I leads C by 90 degrees. So let me try to draw this nicely. So I would cross 0 first, going around in this phasors rotating around an origin description. I crosses first, but what you really see if you were to look on an oscilloscope, if you could look at the current on the oscilloscope, that is, you would see that I in the capacitor crosses 0 before V in the capacitor does. So the current and the voltage are not in phase. The only place that they're in phase is in the resistor. And the current in a series circuit, it would be the same current everywhere. So this is a summary of these relationships, and going into the next section, which I thought confused it a little bit, but this is in the time domain, and in the last chapter we did the transient response to a step. If you made step B and I, we figured out how the circuit would behave. It would be underdamped, overdamped, or critically damped. But now we're in the steady state. These are all relevant things to describe our circuit behavior in the steady state. So always implied is an e to the j omega t, always on both sides of these equations. So this would be in the time domain, how you describe the circuit behavior, and this is in the frequency domain. And we can look at a circuit, which we're going to do in a moment, and we can write equations for each one of the components in the circuit and we can write it in the time domain, or we can write it in the frequency domain. And it turns out it's going to be a whole lot easier to analyze this circuit, at least in the steady state, by considering it in the frequency domain. And before moving on to my next, formally the next section of how your textbook treats everything, I want you to notice something about these frequency domain equations. So if I rearrange the terms here, I have V over I equals R, right? And right here I have V over I equals J omega L. And right here I have V over I equals 1 over J omega C. And this is going to actually be what's really important. What's the units here? Voltage divided by current is ohms. Voltage divided by current is ohms. Voltage divided by current is ohms. But I have J omega L and 1 over J omega C, and I'm telling you right now that the units are ohms. So this has a this leads us into how we are going to define what impedance and admittance is. So let's go on. So the next section of the book then recognizes officially that R has units of ohms, and J omega L has units of ohms, and 1 over J omega C has units of ohms. So we can, instead of calling that resistance, because resistance is a pure real quantity, your textbook now says that that's impedance. But this is not, I mean, in the most general sense of the word, it is really an impedance, but we actually give special terms to just these imaginary portions. So we understand that we can have an impedance in a circuit, and it can be some kind of a complex number, like 5 plus J2. So 5 would come from a resistor value, and 2 would come from a inductor value, for example. And so we can have a resistance that's a complex quantity. But the imaginary part right here is given a more descriptive term called the reactance, and we give it the symbol X. And most of the time we say X sub L for inductive reactance and X sub C for capacitive reactance. So to new engineers, saying impedance, reactance, and resistance gets a little bit confusing. But in all of these cases, the units are always ohms, or admittance is in units of 1 over ohms, which some people call mhos. Yes, I'm not kidding, it's ohms spelled backwards. And or sometimes actually the more official unit is in Siemens, but you will hear it also called mhos. So in the resistive world, this is conductance, and this is resistance. This is reactance, inductive reactance, and this is susceptance. This is capacitive reactance. Here, XC is capacitive reactance, and susceptance is given a B, the symbol B, B sub L, B sub C, and conductance is a G. So it's a little bit confusing. All of them have units of ohms, but if you're talking just about a capacitor or just about an inductor, it's reactance or susceptance if you're doing the inverted version of it. So it can be confusing, but keep in mind all of them in the most general sense are part of an impedance. It's just that when you have an impedance that's purely real, if that's your impedance, like from a resistor, then it's really a resistance, or we give it a special subset name or more specific name called a resistance. If I have a value of X sub C, So let's say it's 1 over omega is 2 pi f. So j 2 pi c, and this has some value. This is a reactance, and what it really means and it's in ohms, it's really a resistance that varies with frequency. So a reactance is a resistance that varies with frequency. It's in ohms. If the frequency, if 2 pi, oops, there's an F missing here. If my frequency gets very, very large, my reactance gets very, very small. So at very high frequencies, a capacitor would behave as a short because the number of ohms gets very small. At a very low frequency, my reactance will get larger. There would be more ohms in the end. So reactance is really, well, it's a subset of impedance. It's always in ohms, and impedance and reactance are both resistance that varies with frequency. That's what it really means. And admittance, which is in the real world, well, it's just 1 over the impedance, the inverse of the impedance. So conductance is the inverse of resistance. So that's why, here we go, conductance is the inverse of resistance. But in the most generic sense, admittance is the inverse of impedance. So impedance is resistance as a function of frequency, and admittance is conductivity as a function of frequency. So how conducting is this circuit as a function of frequency? So let's go on and show how you apply it in the circuit problem. So I'm going to start with this RC circuit and show you how to analyze it in the frequency domain. It's given in the time domain with a sinusoidal excitation, but we'll show you how to do it in the frequency domain. I'm a little surprised that the next section in your textbook has it as an optional section using Kirchhoff's laws in the frequency domain, and to me that's the only way to do these problems. So we will go over the next section also. So when you see a problem like this and you have to you want to solve it in the frequency domain, the first thing you do is just find all of the impedances in the circuit. So Z for this component right here is 5. It's a real number, right? X, which is Z for this capacitor, which is really the reactance of this capacitor, is its resistance as a function of frequency, if you will. So that's 1 over 2 pi f times c. And you can find a value for it in ohms at this frequency. And the frequency in this circuit, f equals, omega equals 2 pi f. And we have omega right here. Omega is 4. So if we want to solve this in the frequency domain, the first thing we have to do is convert this into phasor notation, which is 10. We don't even have to worry about expressing that part. We have no particular phase listed there, so that voltage source in phasor notation is that. In polar coordinates and in rectangular coordinates, it's this, 10 plus J0, right? And this is 5 plus J0. And this one is a little bit more complex because you have to compute that. 1 over, I want to know J actually. Show you how to do this correctly because you have to keep track of all of the phases here. So it's 1 over, don't forget the J here to keep track of your phase. So it's 1 over J, omega is 4. Omega, that should be omega. I'll just put it omega. I get used to writing in frequency sometimes, but let's put it as omega. And C is 0.1, and so it is 1 over J 0.4, which equals minus j 1 over 0.4, which equals minus j 2.5? Yes, 2.5. And it's in ohms. So now it's really a matter of almost like just finding, if these were both resistors, we would have found R total. But now we're going to find Z total, which is going to be Z1 plus Z2. So Z total is Z of the resistor plus, basically it's Z over the capacitor, which equals 5 plus, actually it's minus J 2.5. And that's what the total, it's the total impedance of this circuit, which is resistance that varies with frequency, and at a specific frequency of 4 radians per second. So that's what Z total is. And now we can say, so we have to find V total and I total in the circuit. And so we can apply Ohm's law now. I equals V over I. And we have V, which is 10. Z. We have V is 10 and Z is 5 minus J 2.5. And we know how to do that math. So we can do the math, and when we get the answer, we get I in phasor notation is 1.6 plus J 0.8, which equals 1.789 angle of 26 amps. We're in amps. Let's not forget our units. And if we want to find the voltage just across the capacitor, it's like doing Ohm's law again. So V across the capacitor equals I in the capacitor, which is I the same everywhere, times Z of the capacitor, which is our X sub C. And that equals, oh, I lost my mouse again. My I is 1.789, rewriting it there. And X of the capacitor we found right there is 1 over J 0.4. Now, of course, we have our mixed polar coordinates and rectangular coordinates, so we have to convert that. 1.789 angle 26.57 and divided by 0.4, and with that in the denominator there, the way it is right now, that's a plus 90 degrees. And now we can do that math nicely. We get 4.47 angle of minus 63 degrees. So if I were to draw this on a phasor diagram, which is might be quite useful for you, textbook doesn't emphasize that enough. If I were to draw that on a phasor diagram, I would have, let's do the impedance phasor diagram right now. This vector is R and it equals 5. This vector going this way is, so capacitors are always drawn down. So it's this value right here, minus J 2.5. So XC right there along the imaginary axis is 2.5 pointing down. So it's minus 2.5 J, right? And then I get a resultant Z right here. The resultant Z right there equals 5 minus J 2.5. Now I can make this into a magnitude and phase angle if I want. And if I did, that phase angle would be right here. and that magnitude is the length of that vector. So I'm getting ahead of myself a little bit because it's going to be in the next chapter a whole bunch. We're going to apply all of these concepts to the next chapter and show you how to analyze the sinusoidal steady state. But let me genericize it a little bit as an introduction to the next chapter. So I have here just two generic circuits. One's a series circuit and one's a parallel circuit, and this is actually how you'll attack these problems. Every component, every element that you have in the circuit, and there's some elements in series, every single one of them has a voltage associated with it, and every single one of them has an impedance associated with it. If it's a purely real impedance, it's a resistor. If it's what we call a reactive resistance, a reactive impedance, then it's a capacitor or an inductor. So you're going to go through every single circuit element and you're going to write down what its impedance is. So if it's a resistor, you'll write down its ohms. If it's a capacitor, you're going to write down 1 over omega j omega c for each one. This is the ohms for each one. And if it's an inductor, you're going to write j omega L down. And you'll have the values, and I don't care if it's in series or in parallel, for each component you're going to write down what its ohms are. And it's either going to be a resistance R, or it's going to be a resistance that varies with frequency, so it's going to be a 1 divided by j omega c, or a j omega L. And so at the frequency of interest, you will have the ohms of each element. And then you can generically replace each element with a block, as done here. And then all of our circuit analysis tools apply. All of our Ohm's law, all of our Kirchhoff's laws apply, only all of the numbers are now complex, and you have to do the whole problem with complex numbers. So Ohm's law completely applies, except that our Z is going to be some complex value, and our currents and voltages will be some complex value. That is how these problems are done when you have a sinusoidal steady state. So here's an example. Ooh, my computer is being slow a little bit. I think it's struggling a little bit with how much I'm asking of it in these videos. Okay, so here's an example. What you do, the circuit is operating at 50 radians per second, and what we want to do is replace every single one of these elements with I call it an impedance block. So on this one, I'm going to say that the X sub C equals 1 over j omega c, and same thing with this one, and X sub L equals j omega L. And we're going to compute these. So the 2 millifarad capacitor now gets replaced with X sub C equals 1 over j times 50 times 2 millifarads. And that computes to minus 10 ohms. Complex, or purely imaginary, right? With the minus sign in front of it. The 10 millifarad capacitor, something similar. X sub C equals 1 over j 50 10 millifarads. And it ends up being 10 millifarad capacitor. Calculate it. Minus 2, or minus j minus j2 ohms. And then the inductor, 0.2 henries. We get a reactance from the inductor, and it is j omega L, so equals j times 50 times 0.2, which equals j10. Now, this leg right here actually has a total impedance, which I will call Z1. Now I'll call it Z2. Z2, I'll call this one Z2, is 3 ohms plus this, plus minus 2J. Sorry, I should have put that J first. 2J ohms. And these two guys are in series. So Z3 is 8 ohms plus J 10 ohms. So I can now replace this circuit, which I have to find the total input impedance, or the what used to be in our resistor circuits, the equivalent resistance or the total resistance. So I can say that I have a Z1, a Z2, and a Z3. And I have values for all of those. So these two are in parallel with each other, which is in series with this one. So we know how to do all of that math. So Z in, or Z total, equals Z1 plus these two in parallel with each other, which would be Z2, Z3 over Z2 plus Z3. So just like a resistor circuit, except that you have complex values, these impedances, they're all in ohms and they can be complex numbers, and so we have to obey all the rules of doing complex math. So that's really what you have to do, and now we just plug in the numbers. So that equals, actually it's in your textbook. I don't need to write out all the numbers again, so I'll just paste the answer over here real quick and you'll see. So here it is. So Zn was Z1 in parallel with, or Z1 in series with Z2 parallel Z3. We plug in the numbers, we just have to do the math, and we get a total input impedance right there in the rectangular coordinate system. Now I can also convert that to a magnitude and phase if I want, and your problem didn't do that, but you could do that. You can convert it to a magnitude and phase and draw it out pictorially in the complex space. So there's real and there's imaginary. The resultant of all of this, if you were to draw an impedance phasor, is you have a real component that's 3.22 ohms, and you have an imaginary component pointing downward because it's minus J of 11.07. And so you can actually get a total impedance Z right here, and Z will equal, by Pythagorean theorem, the square root of the real part squared, the resistive part, the 3.22, it's a right angle, plus the imaginary part, the x part, whether it's C or L, squared. And you can get that magnitude, and you can get that phase angle right here, because that would be tangent to the -1 of opposite over adjacent, so of 11.07 divided by 3.22. So often we talk about the phase of a signal, the magnitude and phase of a signal, and so you can express it this way. Oftentimes in practical circuits you'll see it expressed this way. If, well, this circuit has a net total resistance, total impedance with a negative imaginary part, that means that this circuit is more capacitive. The net result is this circuit is behaving like a capacitive circuit, more like an RC circuit than an RL circuit. Even though there's an inductor in it, I'm not behaving inductively. The circuit at this frequency is behaving capacitively, and that will be important as we study things with varying frequencies. One more example. I like this example. So here's the time domain circuit, and it says figure out what V out is, and it's given to you in the time domain. So the to analyze it and find out what V out is in the steady state versus the transient response, mind you. So the first thing you do is you take this time domain circuit and you convert it into the frequency domain down here. So my source I've converted to a magnitude and phase, and then each one of my elements in the circuit I convert into an impedance, whether that's a resistance or a reactance. I have computed it. And so the capacitive reactance is computed right here, becomes minus J25. The inductive reactance, J omega L, becomes J20 ohms. And so I rewrite the circuit with my ohms for each element there, and then by voltage divider principles, V out is going to be by voltage divider principles, V out is the impedance of this parallel combination divided by the total impedance of the circuit times the source. So that's what we've done. But now everything's complex numbers, so we just have to mind the complex number math. And then we get an answer right here that V out is that many volts at that angle. And then to be complete, that you don't leave it, you're given the problem in the time domain, you should answer the problem in the time domain. So V out as a function of t, keeping in mind that steady state, not transient. So t, where t has been allowed, where any temporary transient response to the circuit has had time to settle out, will be 17.15. Cosine omega is 4 for t plus the phase angle volts. Okay. So all of the laws that we have learned for these passive circuits, the Ohm's and the Kirchhoff's laws, Ohm's law and Kirchhoff's law, apply to the AC circuits is the same way they do with DC circuits. That is V equals ZI instead of V equals RI. And you can sum the currents up with Kirchhoff's current law and sum the voltage up with Kirchhoff's voltage law, just the same as you did in a DC circuit, except now all of our numbers are complex. So we have a complex resistance, which is called impedance, which is the real part plus a reactive part. And all of the units are in ohms. And it's basically a resistance that varies with frequency. And we express that in phasor notation when we express it in the frequency domain. Admittance is the reciprocal of impedance. Works well for parallel circuits. So impedance in series and parallel are combined in the same way as we did in series circuits, but now all of our numbers are complex and we have to keep track of the phases that are associated with the circuit, because the currents and the voltages won't be maximized at the same time. So we'll do a lot more of this in the next chapter, and we'll also apply it to some practical examples.